electromagnetism, combustion, compressed air. These are the technological staples which we use today to process and move large masses of stone and other materials. But what about sound? Acoustics. On this channel, we've looked at the possibility of a powerful sonic technology in ancient times, as implied in legends and anecdotal accounts passed down from those eras. And we've seen some hints as to how that might work, at least on a smaller scale. But if the ancients did have a sonic technology that was powerful enough to lift and or propel multi-ton blocks over the Earth's surface, it is also reasonable to assume that that same power would have been leveraged to cut into, carve, and sculpt stone as well. So were huge tuning forks and other acoustic devices used as conduits for this vibratory power? The world is full of the remnants of stone wonders from the ancient past. In addition to moving and raising the enormous stones used in many of these structures, another mystery is how the ancients were able to cut and shape such hard materials. Many people rightly question the mainstream claims that these feats were achieved with nothing more than stone chisels, chicken wire, and lots of time. In the video, Ancient Acoustic Cutting, we looked at a possible solution as to how long cuts into stone could be made with a rotary wire saw, and how perhaps a vibrating, oscillating version could have hypothetically been used in antiquity. But what about the giant carvings of icons such as the Great Sphinx, the Colossi of Memnon, or the statues of Ramses II at Abu Simbel, which have remained fairly intact over the centuries? We could ask similar questions as to how ancient sculptors were able to not only carve into these hard, durable materials, but also how they were able to do so with such precision and detail, especially on such a massive scale. It must have taken quite some time to achieve such techniques. So what techniques and tools did the ancients employ to assist them so that they could complete these massive projects within a lifetime? Perhaps we can get an idea from looking at how some of the modern mega sculptures were produced. Probably the most well-known and iconic among them is Mount Rushmore. Like many large projects, Mount Rushmore was created in stages. The following details of its construction describe a digressive, energetic process, including the use of high-energy explosives in the first phase, to mechanized hammers in the intermediate stages, and more traditional tools in the final stages. It says here that to carve the 4 presidential heads into the face of Mount Rushmore, methods involving dynamite and pneumatic hammers were used to blast through a large amount of rock quickly, in addition to the more traditional tools of drills and chisels. And so we can see here the digression of high-energy tools to low-energy tools as the process became more refined. After achieving the general shape with the aid of explosives, the drillers then removed stone to within 6 inches of the finished surfaces using 75-pound Chicago pneumatic jackhammers. As we know, a pneumatic or air hammer works by using compressed air to drive a piston. The piston hits a chisel or punch, which then breaks or chips the material. Air hammers are powered by an air compressor, and they usually have a regulator to control the air. Once adequate rock had been removed, the carvers would then take over. By drilling a series of shallow holes in a closely spaced grid, and then removing these grids by drilling obliquely, a process which they called honeycombing, the carvers got very close to the finished surface and completed the final stage by using smaller, handheld pneumatic hammers. The hammers were used to first remove the roughness left by the honeycombs, and then to create the defining features such as wrinkles or pits in the skin. Assuming that the ancients used similar processes thousands of years earlier, what would their digressing energy process look like? The builders of Mount Rushmore began with dynamite explosives. But what high-energy methods could the ancients have used, which typically begin the initial large-scale removal of stone? Is it possible that some form of ancient explosives exist in antiquity? Actually, the materials for such devices were certainly available in those times. We might remember from science class that even something as rudimentary as flour or milk powder have the capacity to explode. Flour and milk powder are not explosives in and of themselves, but they are still highly combustible under the right conditions. This is why certain precautions have to be taken at flour mills, as fine, airborne flour particles surrounded by oxygen-rich air and subsequently ignited by a spark or flame can cause the suspended particles to ignite, as we see in the following clips. From this principle, a potent flour or powder bomb can be made by confining the material within a small space, which will pressurize the expanding hot air. A candle is placed within the can, and then it is sealed shut with a small tube running through a small hole in the side. Blowing air into this tube suspends the fine flammable particles within the confined atmosphere inside of the can. The particles with the oxygen will then ignite, and the expanding air from the intense heat generates pressure that is sufficient to blow the top off of the can. It is certainly likely that the ancients would have noticed that the same expansive reactions which occurred when accidentally or purposely dropping fine powders into open flames. Using this principle, ancient observers could have used their great ingenuity to create timed flour bombs. After all, calculations show that 1 kilogram of flour, if ignited efficiently, is energetically equivalent to about 15 sticks of dynamite. We will delve more into the concept of ancient explosives in a future video. But what methods could the ancients have used for the finer carving and sculpting? Perhaps this is where acoustics might have played a role. But what forms would such acoustic carving tools take? What could be the ancient acoustic equivalent of small and large modern pneumatic hammers? As incredible as it may seem, one such form might be that of a large tuning fork. And there have indeed been some alternative science theorists who have suggested that giant tuning forks were somehow used to drill and perhaps even cut into hard rock. But of course, to mainstream scientists, this would be ridiculous. But empirical evidence exists which demonstrates that this may in fact be a possibility. We can see here a small tuning fork with weighted tines. These weights allow the fork to resonate with much more energy. By striking one side as shown, I set the tuning fork into vibration at its natural frequency. Touching the fork to parts of a brick, small pieces of concrete can be broken from it. Also, the broken pieces can be further pulverized. From this, we can envision how a much larger, heavier tuning fork vibrating at resonance could make significant inroads into rocky surfaces. But of course, it is difficult to make much progress with a passive tuning fork. As we can see, I have to percuss it continuously after each touch to the rock, as the vibratory energy is quickly dissipated. By mounting the fork on a wooden board and activating it with a solenoid powered by a function generator, I can vibrate the fork powerfully and continuously by tuning the generator to the fork's resonant frequency. We can now see its improved potential to process pieces of rock, though it still struggles somewhat with a complete rock. It should follow then that a much larger tuning fork could make cutting and carving more effective and efficient. Interestingly, there have been at least one account of giant tuning forks being found in ancient Egypt, allegedly housed in a museum storage area. It is said that there were hundreds of them, ranging in size up to 9 feet. Did these ancient tuning forks make up part of the ancient Egyptians' vast arsenal of tools? The forks were also believed by the observer to have been made of steel. But tuning forks could be made out of wood as well. Wood is quite resonant, as we can see here. When I place a small music box on the board, the sound is significantly amplified due to the board resonating close to a range of frequencies, which include those of the music box. As with wooden musical instruments, the wood can be tuned to resonate with certain frequencies simply by modifying its dimensions. I couldn't find a large metal tuning fork, so I made a makeshift one out of wood. A two-sided solenoid arrangement agitates 2 sets of magnet stacks that are mounted on the insides of each of the fork's tines. The alternating force pattern developed is the same as that of any other tuning fork, with the tines alternately diverging and converging, hence rarefying and compressing the ambient air, as shown in the figure here. Putting the wooden fork into contact with the sounding board, the sound is amplified just as with the music box, but the amplification is not particularly strong. Like any acoustic device, its efficacy relies mostly on the amount of energy which can be efficiently transferred into the system by resonance. And so the attenuated response is most likely due to the operating frequency being significantly lower than the optimal frequency range of the sounding board. The fork also seems to lack power to carve into rock. This may be because wood has significantly less elasticity than metals such as steel and aluminum, which compose most tuning forks. But still, I believe that better craftsmanship might produce a pretty powerful wooden tuning fork. Another modification could be a wood-metal combination. We can see here that I removed the wooden tines and attached 2 12-inch steel brace plates, which take over the function of the tines for the makeshift tuning fork. The resonant frequency response is quite low at about 30 Hz, with the added weight of the chiseling tool to one of the tines, but we can see that it does have decent carving ability. We can compare this to commercial pneumatic carving tools as shown here. The function is practically identical. So my conclusion is that a large tuning fork composed entirely of metal would be at least just as effective, and probably much more so, as the fork would be able to resonate at a much higher frequency. We should also remember that the addition of weights to the tines would greatly increase impact force, but would also lower the resonant frequency. Perhaps we could envision large tuning forks that weigh around a fraction of the 75-pound Chicago pneumatic hammers. Acoustic forks of that size and weight would likewise have to be operated with 2 hands, but might have the same potential to break off large chunks of rock from the surface. Smaller handheld acoustic tools could then be used in the later refinement stages. Acoustic carving tools can take on a number of different shapes and designs. Here is another iteration in which I've attached the chiseling tool by magnet to the vibrating surface of one of the metal can resonators, which I've previously used in various acoustic lubrication experiments. thus illustrating that the same devices used to reduce friction and move heavy objects can also be used to cut and carve into stone. The unloaded can vibrator itself has several resonant modes, including 82 Hz, but the weight of the chisel lowers the overall resonant frequency to 49 Hz. We can see that, like the tuning fork, it also performs the same chiseling action as the pneumatic hammers. But again, unlike the pneumatic devices, this acoustic chisel's vibrations are greatly enhanced by the resonant frequency of the can. This highlights a principle that may make acoustic tools potentially more effective, in that tools vibrating at the natural frequency of a workpiece, or perhaps at a subharmonic of it, would render the carving effect even more pronounced, as there would be a maximum transfer of mechanical energy from the tool to the stone, and hence would achieve the same results with significantly less energy. We may recall this concept from the article highlighted in the video, Ancient Acoustic Cutting, in which scientists found that vibrating stones at their resonant frequencies make them easier to crush and pulverize. And so the same should hold true for cutting and carving. By being tunable to resonate at different frequencies, acoustic devices could potentially cut into and carve an extensive array of rock types with equal effectiveness. With tuning forks in particular, this frequency adjustment might be achieved by making the tines extendable and retractable. Hence, we have concrete proof that sound can literally shape solid stone. This is probably nearly as amazing as being able to cut through solid steel with the coherent light of a laser. Perhaps these examples might make it easier to envision the possibility of using sound in this manner. Ultimately, we must realize that the ancients had the same brain that we have. Expending tremendous efforts just to make only inches of progress each day would have quickly resulted in boredom and eventual apathy, which would become detrimental to such culturally important and vital projects. Hence, it follows that they would have devised and constantly improved various tools and methods to assist them in processing so much raw material and making their burdens lighter, just as we do and continue to do today. We know that the ancients were fantastic observers of nature. And so what if it were possible that they observed the power of sound and found a way to harness it to help them move and manipulate large blocks of stone? What if they used sound vibrations just as we use electricity and electromagnetism? The next obvious question then would be how the ancients would have powered such vibratory devices. We'll explore this question in an upcoming video, which will be entitled A Hydroacoustic Power Plant. Thanks for watching, and as always, stay tuned.